to all students. Today we are going to study about rotating magnetic field produced by the three-phase supply. In the previous lecture, we have studied the rotating magnetic field produced by the two-phase supply, where we gave the two-phase supply to the two different windings to produce the two fluxes, and both fluxes were produced at an specific displacement of 90 degree. So that displacement in two fluxes caused to produce the rotating magnetic field. So we studied that what are the basic cause, what are the basic reasons for producing the rotating magnetic field. So there we used the two-phase supply for producing the rotating magnetic field. Now, as we are going to study about the three-phase induction motor, where there are used three windings in three-phase system. So rotating magnetic field will be produced by the three-phase system. So there are three coils. Each coil will produce the separate magnetic field, and each coil is placed at a 120 degree apart from the other coils. So magnetic flux will also be produced proportional to those fluxes or those coils. So what would happen here? Magnetic field produced by the three coils will be at a 120 degree apart, which will cause to produce the magnetic field in rotational mode. Its magnetic field will be rotating, so that we call it a magnetic field produced by three-phase supply, which is a rotating magnetic field. And there will also be the specific speed of that magnetic field, and the speed at which our rotating magnetic field rotates, that is called the synchronous speed. But we are just going to study about the magnetic field produced by the three-phase supply, or three-phase supply produces the magnetic field which will be in the rotational mode. So that it is called the rotating magnetic field produced by the three-phase supply. So let me draw the diagram for it. So first of all, rotating magnetic field rotating magnetic field produced by three phase supply. It means rotating magnetic field, the name which has been entitled how does it produce, will go through it. So first of all, we will draw the three-phase system. So three-phase system can be drawn in the two different way, as we know. First one is a star connection. Second one is the delta connection. So we draw the star connections for the three-phase system. So we will do the three coils. So here there are three coils. Coil number one, which is denoted by R. Coil number two, which is denoted by the Y. And coil number three, which is denoted by the B, which is basically known as a red, yellow, and blue. These are the standards denotions for the three-phase system, whether it is a three-phase machines or a power system. These are the basic denotions which used for all. R, coil number one is denoted by the red, coil number two, which is denoted by the yellow, coil which is denoted by the B. So three coils are supplied from the three ends. So this is called three-phase supply. We have given three-phase supply to it. Now we have given three-phase supply to the three coils. And three coils are placed at a specific angle. So suppose we will go through that angle. So what is the denotion? Coil 1 or coil R is placed at a 120-degree apart from coil B. Or sorry, coil Y or coil 2. Coil R is placed at a 120-degree displacement of coil Y. And coil B is placed at a 120-degree displacement from the coil Y. Similarly, coil number B is placed 240-degree apart from the coil R, and coil B is displaced 120-degree apart R in opposite way. So observe, all coils R, Y, and B are placed at an 120-degree apart. So coil R will produce the flux phi R, coil Y will produce the flux phi Y, and coil B will produce the flux phi B. We are not going to study about the alternating quantities like voltage and current. These voltage and currents produce the magnetic flux. So we will study about the magnetic flux produced by these coils. So basically, if I will write the flux produced by the R, so what would I write? I will write phi R. Phi R in the alternating way. So there will be the sinusoidal quantity. We have supplied the three-phase AC. So three-phase AC supply is given. So that will be the alternating quantity. So alternating quantity is represented by phi m sine omega t. Okay, so the magnetic flux which has been produced by the coil R is a phi R. and its value is selected as a phi m sine omega t, which is assumed as a reference value. Now, next flux will be produced at a 120-degree apart because of second coil is placed 120-degree apart or displaced from the coil R. So flux produced by the Y coil will be 120-degree apart or displaced. So second flux will be denoted by phi R. Sorry, phi Y. Second flux will be denoted by phi Y, and phi Y will be denoted as a phi m sine omega t minus 120-degree. Next, phi y is written in such a way that phi m sine omega t minus 120-degree because of it is 120-degree behind the flux phi r. Because of its coil is also placed 120-degree behind the R. Similarly, there will be the flux phi B, which will be produced by the coil B. There will be the third flux phi B. So phi B flux will be produced by the coil B, which is at a 240-degree from the flux phi R. Means coil B is placed 240-degree apart or displaced from the coil R. So its flux will also be displaced around 240-degree. So phi m sine omega t minus 120-degree plus 120-degree means total minus 240-degree. So we have seen that coil R produces the flux phi R, which is considered as a reference value, and we will consider the other coils and other fluxes produced by the particular coil with respect to the R coil and R flux. So phi R flux is considered as a reference. So phi R equals to phi m sine omega t, coil number Y, which generates the phi Y, which is at a 120-degree. So phi Y equals to phi m sine omega t minus 120-degree, and phi B, which is produced by the coil B, which is placed 240-degree apart from R and 120-degree apart from Y. So we have written it as a phi m sine omega t minus 240-degree. So 240-degree means it is placed 240-degree from the R. But if we consider from the axis Y or coil Y, so it is placed 120-degree displaced from the Y. So now we will place or draw the vector diagram for these three phases. So let us place or draw the vector diagram for these three phases with respect to their fluxes phi R, phi Y, and phi B. So in the next term, vector basic vector presentation basic vector presentation will be like that. There is a R phase. R phase will produce the flux phi R. So I will draw as a reference. This is our phi R. Okay, I represent it as a vector R. So next, Y coil will produce the flux phi Y. So phi Y flux will be at a 120 degree from the flux phi R. So 120 degree behind means lagging. So we will draw the phi Y lagging the phi R. So lagging means this is 90, this is 90, and this is about 120. Okay, so this is phi Y, phi Y, and next 30 has been covered, and this is then 60. 60 plus 60, 60 plus 60, another 120. So our next coil will produce the flux phi B, and phi B is at a 120 degree, or 100, phi B is at a 120 degree from the phi Y, or 240 degree from the phi R. So let me consider right now the phi Y. So I have means we have to consider the displacement of 120 degree from the phi Y. So from the phi Y, we have to consider 120 degrees. So this is our 60. This is 60 degree. So next is 60. This is our B phase. And this will produce the phi B. So as we see that all the three coils are placed at a 120 degree apart, and their fluxes are also at a 120 degree apart in mathematical form. So their vectors are also 120 degree apart from each other. So there is a displacement of 120 degree. This is 120 degree displacement. This is also 120 degree displacement. This is also 120 degree displacement. So as we see that three coils will produce the three fluxes, and all the three fluxes will be produced 120 degree apart from each other. Means all the fluxes are at a 120 degree displaced from the other fluxes, which have been observed from the vector representations, which have also been observed from the mathematical views or conditions, like a phi r equals to phi m sin omega t. This flux is 120 degree apart from the phi y and phi b. Similarly, phi y is also 120 degree apart from phi r and phi b, and phi b is also 120 degree apart from the phi y and phi r. Now, we have seen the basics three-phase system or star connection. And star connections will have three coils. Three coils will produce three different phase fluxes in them. And these fluxes will be produced 120 degree apart from each other. Now, we will see how will be their quantities presented on the graph of sinusoidal waveform. If I will place the all three fluxes phi r, phi y, and phi b in the sinusoidal waveform, so how will it appear? How will it look like? So I can understand that what is happening of the alternating fluxes and how do they behave. That can be understood with the help of graph between the maximum flux or flux and time. What we have studied in the alternating quantities. Let's draw. This is T. This is considered as a phi m. Okay. I place one envelope by which quantities will not go beyond that. So let us take one quantity R. This is R. Second will be drawn Y. This is yellow. R, Y, and B. Actually, it's black. Let me draw it as a black. So this is your so we have drawn the diagram for the three different fluxes, which are as a phi R, phi Y, and phi B. So as we have already discussed that all the three fluxes are 120-degree apart. Fluxes are 120-degree apart from each other. These are the fluxes which are represented in terms of alternating quantities on the time and flux axis. So value of these can be studied with the help of little mathematical conditions. So we will keep certain conditions. So to place certain condition, we have to fix the some point on this graph or over these graphs. So we will place some conditions or we will place some instant over this graph to determine the particular value of the fluxes. So these fluxes are in the form of alternating quantities. And these are in the sinusoidal waveform. So we will remember one condition. So that condition will be that condition would be that these are the alternating quantities, and alternating quantities are represented in sinusoidal form because of these are sinusoidal quantities. So sinusoidal quantities will be represented in terms of flux. So sinusoidal fluxes are in the sinusoidal form. So this is, and all the sinusoidal quantities or all the fluxes in sinusoidal quantities are at a 120-degree apart. So flux phi m or phi r. Suppose I will define phi m here. Phi m sin omega t. So sin omega t means all fluxes are 120-degree apart from each other. So phi m into sin omega t. Omega t. Omega t means 120-degree because of phi r is at 120-degree from phi y, and it is also 120-degree from phi b in reverse mode. But phi y is also 120-degree apart from phi r and phi b in two different mode. So each flux is at a 120-degree displacement from the other fluxes. And those are the sinusoidal quantities. So we will keep the common value, that is phi m into sine 120 degree. Phi m sine 120 degree. So phi m sine 120 degree can be written as a phi m under root 3 by 2. So wherever there will come the point to place the quantity of flux, so we will select this quantity, whether it is phi r, phi y, and phi b. So under root 3 by 2 into phi m. So in the other sense, I will say phi r equals to phi y equals to phi b equals to phi r equals to phi y equals to phi b equals to under root 3 by 2 into phi m. It means all these are the alternating quantities. Those are in sinusoidal waveforms, so that alternating quantities are at the certain displacement. So we have considered sinusoidal alternating quantities in terms of flux with respect to its displacement. And there are common displacement of 120 degree. So all fluxes will be represented by the under root 3 by 2. So this will be remembered. We will place in the vector summation or resultant vector this value. These conditions will be remembered as I have spoken, that phi m into sine omega t fluxes are in sinusoidal waveform. So sinusoidal waveforms are represented with angle to determine the specific value. So here all fluxes are at a 120 degree. So we have simplified it. So phi m into under root 3 by 2. So this will be under root 3 by 2 into phi m for a specific value. So phi r equals to phi y equals to phi b equals to under root 3 by 2 phi m. So we will keep these conditions in our mind. Okay, so let me draw it properly. It is under root 3 by 2 into 5. Now, we will see the conditions with vector summation, but how do we study this? How do we observe these diagrams? So to observe it, we will place certain point over this graph to observe all the quantities phi r, phi y, and phi b. So I denote 4 different quantities. So this is point instant 1 first. This point is instant 2. This point is instant 3. And this point is as an instant 4. This, 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 and this. So over the half cycle of phi r, what are the values of different fluxes? We will observe that. So what are the values of phi r, phi y and phi b at the instant 1? Similarly, what are the values of phi r, phi y and phi b over the point 2, 3 and 4 or over the instant 2, 3 and 4? Instant is considered with respect to time or point, whatever we consider. But we have studied same thing in the rotating magnetic field produced by the two-phase supply. We selected the specific instant over the half cycle. Here we are also going to select the specific instants over the half cycle. So let us first of all go through the instant one. At the instant one, at the instant one, we will draw the vector diagram. At the instant one, you see that and you observe that phi r is 0. Value of phi r is at a 0 value. But value of phi b is in positive and value of phi y is in negative. So we will draw the vector of only two quantity. First one phi y and phi b. Phi r is at a 0 values, phi r will be neglected. So we observe the our standard vector what we have elected or we have drawn. So this is phi r, which is at a horizontal axis or 0 axis. From that 120-degree y axis and from r axis 240-degree b axis or phi b. So phi r, this axis will not be drawn. So phi r is 0. This phi r, this quantity phi r is 0. So I will or we will not draw it. So this is neglected. Let us remove this. Now what is remaining? Phi y. But phi y is in negative direction. Phi y is in negative direction or negative half cycle. So phi y is downward. So we have to draw it upward, means we have to represent the phi y in positive way. So specifically we have drawn it downward or in the third quadrant, but we have to draw opposite to this. So y will be drawn like this. Okay, this is our phi y and it is in opposite direction. So I will denote it as a O A. Similarly, we go on the graph. So what do we observe? Phi B, phi B is in positive direction. So where is phi B? is drawn like this at a in this direction. So we will phi b is positive, so we will not change its direction. It will be drawn as it is. So I have drawn it as a this. So now this is OB, OB and flux phi B. So we have selected two fluxes, phi Y and phi B, because of at the instant one, phi B is in positive, phi Y is in negative. So phi B, this phi B has been drawn as it is, but phi Y has been reversed in vector because of it is in minus. Phi Y is in minus, so that we have reversed it. Now we have two vectors. One is phi Y and phi B. Now we will take the resultant of it. So to take resultant of it, we have to draw one straight line perpendicular to the O. So when we will take one line perpendicular to the O, so it will be drawn like this. This. So this is OC. Let us assume it is a OC. Now, if we divide the OC by half, so it will be drawn like this. So OC will be divided by OD. So this is OD. Now, there is a difference of 30 degree. There is difference of 30 degree between OA and OD. And there is also difference of 30 degree between OC and OB. Okay, so total angle difference between the OA and OB is 60 degree. This is total 60 degree. So now, as we see from the resultant, what is seeming? It seems like that OC is the resultant vector. OC is the resultant of two vectors, OA and OB. In other term or simple language, I can say that OC is the summation of OA and OB, but it is not a summation. It is the kind of summation. In mathematical way, we call it as a resultant, which is defined by the different way. So if I will solve it, so what will happen? OC is the resultant quantity, which is the resultant of OB and OA vector. So OA and OB vector has been represented by OC finally. So I will write OC. So what is OC? Resultant flux. Resultant flux equals to OC. Resultant flux equals to OC. So OC equals to 2 OD. If it will be divided into the two parts, so it is 2 OD. 2 OD. OC equals to 2 OD. Now 2 OD will be further divided. So 2 OD is equals to the OA. OD is equals to OA. So 2 OD equals to OA. OA. But OA is at a specific angle from OD. OA is at a specific angle from the OD. So that is cos 30 degree. Angle between the OD and OA is 30 degrees. So I will write it as a 30. So 2 OA. So OA is what? OA is a magnetic flux produced by the coil. So we have already discussed that phi r equals to phi y equals to phi b equals to under root 3 by 2 phi m. So any of the fluxes will be assumed as a phi under root 3 by 2 into phi m. So this is considered as a OA because of OA is our vector. And what is vector? Vector is our flux. Flux has been represented in terms of vector. So flux of OA. What is OA here? Means phi y. Phi y is considered as a OA. So OA value is under root 3 by 2 into phi m cos 30. Value of cos 30 is under root 3 by 2. Value of cos 30 is equal to under root 3 by 2. Now we have to simplify it. 2 will be cancelled by 2 and under root 3 whole square under root 3 whole square divide by 2 will draw it on the next page. So what will happen? Under root 3 whole square divide by 2 into phi m. Okay. So under root 3 square will be 2 has been cancelled, divide by 2 only. So under root 3 will be cancelled. So what will be 3 divided by 2 into phi m. And thereby resultant field or resultant magnetic field equals to 1.5 times the actual magnetic field. Resultant magnetic field is 1.5 times the magnetic field produced by the one coil. Means resultant magnetic field is higher than the magnetic field produced by the single coil of each coil, each system. Okay, so now this is at instant 1 what we have seen. Now we will see instant 2. Instant 2. So at the instant 2, at the instant 2, our phi b is 0. Flux phi b is 0 and flux phi r is positive and flux phi y is still in negative. So we will not draw phi b because of phi b is now 0. So this vector is 0. So phi b vector will not be drawn. We will draw only phi r, which is positive. Phi r is positive, so phi r will be drawn as it is. Phi y is in negative. Let us see. Phi y is still in negative at the instant 2. So phi y will be drawn in opposite direction. Means phi y will be drawn opposite to this direction. Means it will be drawn upward. So let us draw it at the instant 2. At the instant 2, we will draw two vector. First one is phi r, which is represented as a OA, and next phi r is in positive half cycle. Phi y is in still negative half cycle. So phi y is in negative half cycle. So actual vector of phi y will be opposite. Means it is drawn like that. Okay, this is our phi y vector. Phi y vector, it means it is considered as a B. Let us draw the resultant of it. So resultant of it will be okay, OA and OB. Resultant of OA and OB is a OC. OC is the resultant of OA vector and OB vector means vector. OC is the resultant of two fluxes. OA means phi r, OB means phi y. And if it will be OC is divided into the half section, so it will be OD. What we have done in the previous section. So OC is divided into the half section. So OD is equivalent to the OA. So resultant resultant flux equals to OC. Resultant flux equals to OC. OC is equals to 2 OD, because of this is 30°. This is another 30°. So that is total 60°. So OC equals to 2 OD, 2 OD, and 2 OD equals to, what is OD? OD is parallel to the OA. But OA is at a 30° from the OD. So 2 OA equals to cos 30. So 2 OA equals to cos 30. So 2 OA is what? OA is the vector of flux phi r. And we have already assumed that phi r equals to phi y equals to phi b equals to under root 3 by 2. So each flux will be considered as a under root 3 by 2. So phi r is the flux produced by the coil phi, produced by the coil r. So 2 phi OA equals to under root 3 by 2 into phi m. Cos 30 means under root 3 by 2. So it will be cancelled. Next step will be under root 3 all square divided by 2 into phi m. So what will be? It will be 3 by 2 phi m. Means resultant field, resultant magnetic field equals to 1.5 phi m. So in this case, we have also found that resultant of phi r or phi y or vector OA and OB is OC, means resultant of phi r and phi y is 1.5 times phi m. Resultant of phi r and phi y is 1.5 times 1.5 phi m, means any of the fluxes produced by the coil R, Y, and B. So its a fluxes is less than 1.5 times the resultant flux. So resultant flux is 1.5 times more than the single flux produced by the single coil. R resultant magnetic flux equals to 1.5 times phi m. So this is our RMF. Next, at the instant 3, at the instant three. At the instant 3, we will observe that phi y is 0. Means this vector is 0. Phi y is 0, but phi r is positive and phi b is negative. Now phi b is negative, phi r is positive. So we will draw phi r as it is. Phi r will be drawn as it is. This is O A phi r. Okay. Next, phi r is positive, so we have drawn phi r as it is. Now phi y is 0, so this vector will not be drawn. Phi b is negative, so so this vector is drawn opposite to its position. Phi b vector will be drawn opposite to its current position. So let me draw it. So this is its opposite O B. This is OB vector. This is called phi B, and we will draw resultant of it. So this is OA vector, this is OB vector, and this is OC vector, which is resultant of OA and OB. And now, as usual, we can divide it. OC vector is divided into the OD vector. So this is 30°. This is another 30°. And this is 60°. Okay, 30, 30, total 60°. Now, what is our resultant flux? Resultant flux is equals to OD. Resultant flux equals to OD, and OD is equals to resultant flux is equals to OC. Resultant flux is equals to OC, which is resultant of OA and OB, and OC is divided into the OD. So we can write we can write 2OD. 2OD, and 2OD is further divided or simplified into the 2OA, sorry, OD. OD is parallel to the OB. So earlier we were taking OA, now we will take OB. So both are same, quantities will be same. So OB, angle between OD and OB is 30 degree. So cos 30 degree. Okay, so 2OB cos 30 degree. So now 2. OB is the quantity which is the flux phi B. So phi B will be represented by our condition phi R equals to phi Y equals to phi B. Our condition will be placed here 2 into under root 3 by 2 into phi M. Cos 30 will be considered as a under root 3 by 2. So this will be cancelled. Under root 3 whole square divide by 2 into phi m. So our resultant value will be 3 by 2 3 by 2 pi m, which is written as a 1.5 phi m. So resultant magnetic field is equals to 1.5 times of phi m. So as we have seen, the three instants 1, 2, and 3. In the each and every instant, we have observed that only two fluxes contribute at a one time, and that two fluxes result into 1.5 times phi m, means resultant flux is higher than normal flux value. But all the fluxes in the resultant mode produced is not a stationary. As we have seen that resultant flux is produced by the two fluxes. So at the instant 1, our resultant flux OC is at a vertical position. It is completely perpendicular to the horizontal axis. So resultant flux at the instant 1 is vertical or perpendicular to the horizontal axis. But if we will observe or see the instant 2, so at the instant 2, your flux has been shifted 60 degree. This is considered as a suppose this is 90 degree. So this is 30. So 30 plus 30, 60 degree. From this angle, it is around 60 degree. So our resultant flux at the instant 2 has been shifted by 60 degree. It is not stationary at the instant 2. Similarly, if we will move at the instant 3, so what is the condition? Our flux or resultant flux has again moved by 60 degree. At the instant 3, our flux is moved. Sorry, our resultant flux has moved another 60 degree, and it is 1.5 times phi maximum of maximum. We have observed that, or we have seen that our flux is produced by the contributions of more than one fluxes, which is the higher than normal value of fluxes, and our resultant flux produced by the more than two fluxes or two quantities will not be stable, it rotates. So that we have observed that resultant flux produced by the three-phase system does not be stationary, it rotates at a specific speed, or it rotates within the space. So here we have considered or seen the three steps or three instants. Let us see in short at the instant 4. So at the instant 4, what are the conditions? At the instant 4, you observe that phi r is 0, means phi r means this axis will be neglected, phi r will be neglected. Phi r is 0, phi y is positive, means phi y will be as it is. So let us, as it is, this axis phi y will be as it is because of phi y is positive. So let us draw phi y. So this is phi y o OB will be considered, OA will be considered, whatever. Phi at the instant 4, your phi y has been drawn, and at the instant 4, phi b is in negative and phi r is 0. So phi r will not be drawn. We will just draw the phi b, and phi b is in negative, so its direction will be reversed. It will be so suppose phi a OA, and it's a resultant OA vector, which is considered as a, this is phi y and this is phi b, which is in negative. OA vector, which is in negative, which is denoted by phi b, and OB vector, which is in positive half cycle, which is denoted by phi y. So either I can consider it or consider this way. So this is total angle is 60 degree, and angle between OC and OA is a 30 degree. And OC is divided into the two parts, so that is OD and this is again 30. This is again 30 degree, means total is 60. Okay, so any of the vector will be considered for resultant. So resultant field is equals to OC. Resultant field is equals to OC, which is the resultant of or vector summation of OA and OB. So OC will be divided into the two part, which is written as a 2OD, and 2OD can be further written as a OD is equivalent to the OA or OB vector. So either I will consider OA vector with respect to OD, or I will consider OB with respect to OD. So let me consider OA. So 2 OA into cos 30. So we will solve like earlier. So 2 under root 3 by 2 into phi m into under root 3 by 2. So if you will solve it, so it will be 3 by 2 pi m means 1.5 m. So we have seen that from the instant 3, instant 4 represents that OC vector has been shifted another 60 degree. So it means that we observe the instant from the 1 to 4. So at the instant 1, position of resultant vector or resultant flux is vertical. Then it will be shifted by 60 degree, means it has moved 60 degree. The next vector or next resultant vector has again shifted to the 60 degree, and next resultant vector is again shifted to the 60 degree. It means that your vector has been shifted from 0 to 180 degree because of we have studied for the half cycle from 0 to 180 degree, and we have considered the 4 instants at a regular interval for the half cycle, and all the 4 instants have given us the resultant value of the fluxes, where 2 fluxes have given the resultant value with respect to the vector representation or by the vector representation. So vector representations have shown that resultant of all the fluxes at a particular instant is about 1.5 times the phi m, and it does not remain stationary. Resultant vector moves at the displacement of 60 degree, which can be observed here. At the instant 1, it is vertical. At the instant 2, it has shifted to it has shifted around 60 degree. At the instant 3, it has shifted another 60 degree, and it has shifted another 60 degree at the instant 4. Means throughout the half cycle, we have studied and observed that vectors have been in rotation. So it indicates or it proves that magnetic field produced in the space by three-phase system rotates in the space at the displacement of 60 degree. So whenever we give the supply to the three-phase system, so magnetic field produced by it will be rotating magnetic field. It will not be the stationary magnetic field. So this has been learned by us. Whenever we give three-phase supply to the three-phase system, these three-phase system will produce the three fluxes, and all these fluxes will produce the magnetic field in the rotation mode, so that these are called the rotating magnetic field produced by the three-phase system. Similarly, what we have studied in the previous lecture, magnetic field produced by the two-phase system is also rotating magnetic field. It is not stationary. So here we have proved that rotating magnetic field produced by three-phase system is like this. It is not stationary, it is rotational. That's all.